Okay, yeah, so if you have your homework in lab, you could turn that in. And so let's see, that is this homework 3 or 4?
Three.
Okay, that's what I thought. Somebody said homework 4. But
And we can turn the lab in on Thursday,
Homework
right?
4 was posted, so hopefully they didn't do that instead.
what?
Well, you posted that homework lab.
Well, you should do 3 before you do 4, okay? So this is homework 3. Somebody, Rihanna? Yeah, 3.
Oh, I thought you did 3. That's fine.
Okay. All right, so as far as homework 4 goes, I don't know if any of you looked at the website, but I was thinking that we'll have that change the due date till the 27th. I won't cover that material on the midterm next week. So since I'm not going to cover that material, I thought just extend that so you don't have a mad rush for getting that done. We will cover that material prior to the midterm today and tomorrow or Thursday, so you'll be able to do that assignment if you can get started on it. It's not too difficult. It deals with coherence and various issues related to that. So again, the midterm itself will be next week, the 22nd, which is the Thursday. And for this, you can have one sheet of notes, like a piece of paper like this with on both sides. So there's a lot of a lot of equations and things and ideas that we've been going through. So, and the idea of the sheet of notes is that it kind of forces you to figure out what was important in the class. I will post a list of topics that you'll be responsible for. I'll try to get that up before Thursday on the D2L site. And also on the site is a copy of last year's midterm exam, so you can have a look at that. And on the 20th of October, we'll review the problems for that, the solutions, and how to take care of that. So why don't you have a look at that midterm, prior to next Thursday, or I'm sorry, not next Tuesday, and then we'll go over it. And then if you have questions on that or other things, we can go over that on Tuesday. All right. So that's kind of the schedule up until then. So does anybody have a problem with the Thursday exam date? I'm going to keep that exam date, but if there was like major issue with like 3 other midterms or something that day, I could help you out a little bit, move the time around or something on Thursday. Okay, that's fine. All right, so again, the midterm is going to covers up through the imaging discussion that we'll finish today. I have just a couple of minor areas that I wanted to cover for that. So any questions then on the, okay, didn't think so. So again, so what we were doing last time, we were kind of looking at ways of correcting aberrations. And so we wanted to make a Fourier transform holographic lens. So we would have a collimated beam coming in, and then when we reconstruct this with the conjugate beam coming out, we would focus the light down to a point. So the way that, and so to do that, we pre-aberrated the reference beam here. All right, and so you can see with the computer-generated hologram that had in it the correct formation of a quadratic phase function that will give us a kind of a wider field of view with good imagery. Now, in that formulation, if you recall, we had both we had sort of the opposite of this spherical wavefront and the quadratic phase function in that. So the question is, why do it that way? Why not just have the quadratic phase function in that CGH when you replay it, right? I mean, if that's what you're actually recording, why not do that and then just have a plane wave coming in for your reconstruction? Well, I believe the reason is that if you just put the quadratic phase front in that computer-generated hologram, you probably end up with a problem of not having enough features defined in that phase function. So when you make this CGH, you'll have features that you would form. Usually this is all done with some type of lithography, and you have a mask and you form maybe multiple steps or single step. If you form a single step, we'll talk a little more about this later, but if you just have a single transition, so let's say we just had transitions like this. So let's see, if we were making something like a Fresnel lens, you might find something like this where you had or making a lens function, you'd have something like this where you'd have kind of a more planar phase function here. These, by the way, are, this has a refractive index n, and this might be a substrate here. So you make this by lithography. You can use standard reactive ion etching techniques and so forth. Up on the 7th floor, there's a mask aligner if you want to do, various multiple steps and so forth to make higher efficiency. But with this single step, you can get about a 41% theoretical maximum efficiency. So my thought is, though, that the reason why they did it, where they had recorded in there the quadratic phase plus the spherical phase, was that this variation here was a little bit too slow. So you may only have had, something like this and maybe something like that. I don't know exactly what the phase function would be, but you may not have had enough transitions across that aperture to make a decent efficiency diffraction process occurring. And so to get around that, they recorded two functions and then encoded this spherical beam in the hologram to cancel that function that went into it. Okay, I've been thinking about that for a while, and I think that's the reason why they did it that way. Okay, because it's a problem if you have too high a frequency that you're trying to record, because then you're limited by the resolution limit of your lithography process. So that's an obvious one. But there's also some limits on, if it's too slow. I mean, what if there's just one transition? If this is a really slow quadratic, then you have a plane. You can't encode that quadratic. So I think this is the way that they accommodated that, because they're not having that great of a curvature in that quadratic function for this particular application. So anyway, I don't know. I think somebody asked that question or whatever. Anyway, I was thinking about it, and I kind of went through that paper again, and I'm pretty sure that's the reason why they did it. They didn't specifically say that's what they did, but I think that's the reason why they did it. So nonetheless, you're able to get a pretty good correction. So this would be if you're recording just with the spherical wave and a planar wave here without all this. So you would end up with something like this, where if you tilt off at 10 degrees, you start getting a pretty severe coma occurring there. Whereas with this correction, you can go 10 or even 20 degrees and only get, a couple of micron degradation in that reconstructed spot size. So again, it's a pretty useful technique for this correction process. There's some other corrections you can do just with analog holography, just making the holograms in the material with the interferometric exposure. And so this is an example of one such correction that we did in our lab. This was actually for one of the solar concentrating applications. So what we were trying to do here, we put a hologram, just a planar, fringe hologram in combination with a lens. So the lens takes in the power and focuses it. So again, if we did the power in the hologram, that would incorporate or start to show some additional aberrations. So rather than do that, we just made a planar grating with a very simple lens combination here. Now, so this is a spherical lens. It's a simple lens. And the problem that you get with just a simple spherical lens like that is you end up, we were talking about our aberration coefficients. Well, for this spherical lens, you get your spherical aberration, coma. We also get this field curvature. And so the images or the focused regions that you would end up with here are now not on a plane. So again, so what we wanted this for was we would put different PV cells, these different locations, here. So this one would respond to, say, lambda 1 and lambda 2 and lambda 3. So, and this would give us what's called a spectral splitting or spectrum splitting system, and whereby we can get higher overall efficiency by having more cells to cover the solar spectrum, which is pretty broad. It ranges from about 350 out to about 2 microns, where most of the power density in this solar illumination spectrum is. If you try to do that with a single bandgap cell, you can only capture about 33% of the efficiency due to thermal considerations. There's a very famous paper written in 1961 by Shockley and Quasar. Bill Shockley, Nobel Prize winner for inventing the transistor, and Quasar, and they formulated this. They did this analysis of this problem and found with a single bandgap cell you can only get 33%. But if you have multiple junctions, then you can capture more of that illumination. So the problem, though, is then these are different wavelength bands, these big arrows that we have here. And so they start to spread, and that kind of limits your ability to realize a decent system with these multiple cells. So what you can do, all right, so this is if you record the hologram here, say with these two plane waves, right? So you have plane wave here and a plane wave off axis coming in to give you that diffracted beam. Now, what if instead you record the hologram with with points on this plane, all right? So if you put the point on the plane, and now you're going to have the beams going from right to left here. Okay, so when you do that, now the beam that it goes through the lens and it is now aberrated, right? It's aberrated by an amount which corresponds to that difference that you had between this stigmatic image plane, which is actually a curved surface, and this plane, all right? So this distance here now is showing up and producing an aberration, much similar to what we had showed last time for that astigmatism and Petzval or field curvature term. This is a good example of how that shows itself, manifests itself. And so now when the beam comes out of the lens, it's not plane like it was here during the recording, but it's aberrated by exactly the correct amount to correct for that aberration that you have here, or that's produced by this spherical lens. And so when you record that and then reconstruct it with a beam that comes, again, left to right, now you have this pre-aberration going into that lens, and it will come to focus on this plane. Sort of like magic, but it's phase conjugation, okay, is what it's called. So it's a pre-aberration. They do it a lot. You can do this kind of thing in the atmosphere. Astronomers do it all the time for correcting for disturbances in the atmosphere to some degree. They kind of characterize what that is, and then they could put kind of a pre-aberration into the optics that they use to do the recording. Jim Burge actually here has done a lot of work on making holograms to do this pre-aberration kind of process for correcting for some of the atmospheric effects. So you can do this for a lot of different types of aberrations in holography, and it's one of the really great benefits of using a holographic process. Okay. So one of the issues here, though, is that you kind of try to do this over. So for the solar application, you're still kind of at a loss because you have to make this work over a very large spectral bandwidth, right? So you're still going to get aberrations in there. So what you can do, though, is you can make a compromise and kind of reduce the aberrations very considerably. And this is what one of my former students, Juan Russo, had done as part of his research work. So anyway, we're going to now look at another approach towards this aberration correction for wavelength differences. And so before I leave that, if you're interested in solar, I teach for our undergrads 414A and 514A in the spring semester. You don't have to have really any prior knowledge of solar, but if you're interested in learning some things about it, I teach that class, and it's usually a lot of fun, and I think you'll get a pretty good background of some of the major issues in photovoltaics. Okay, so what I want to look at now is again another problem in wave aberration correction. All right, and this problem is a really prevalent one in holography, and so that is that you have a recording material that's sensitive, in one wavelength range, and most of the photopolymers, the ones we have actually were sensitized in the red, but a lot of materials that we work with, like dichromated gelatin, for instance, has a kind of a peak sensitivity out here around 500 nanometers. So if you use 514, it starts to fall off. 532, it's pretty far down, which is double Diag laser. 488 is very good. So argon, that's why holographers like to use argon lasers, because we have these lines that pretty much cover lots of materials. If you have a photoresist falls off. You can't even use 488, but there is a 457 line in the argon laser, and there's also diode pump solid state laser that produces a 457 now. So there are some lasers now that can operate there, but the problem is a lot of times you want to use it at a different wavelength. Say you're recording this in the blue-green, but you want to use it in the red, all right? So when you have that kind of a difference, if you're making a planar grating, right, as we saw before, if you have a planar grating, no problem, right? So here is our planar grating, so K1 and K2, you form that grating vector. If you have a shorter wavelength, all that's going to do is it'll change your angle. You have to redesign it at a construction wavelength here that gives you, say, the angle that you want at the red wavelength here. So here's your red and here's your, say, green. So you can do it if you have a planar grating hologram without any problem at all. However, when you make say a holographic lens, right? So make your holographic lens like this. Now, so you have a plane. You can think of this as having a planar grating here. You have a planar grating here, and you have another planar grating here, and they all have different orientations. All right, so you may be able to match in the center here, reasonably well, but when you start going out here at different radii, you get into trouble, and you start getting these off-axis aberrations that occur and that we talked about last time. All right, so what do you do? All right, so again, we have this this sort of phase transformation characteristic of the hologram, where again, so we can have something like we have our phi O minus phi R. When we illuminate that, we end up with the phase function for the image, right? Image field that we're trying to generate. And again, that might correspond to, if we're reconstructing this again with the conjugate, it'll correspond to what this image is here. But in the case where we reconstruct this at a different wavelength, we may have a pretty aberrated image here, which is not going to be very helpful to us. All right, and again, this is a really common problem because of material sensitivity, like lithium niobate, for instance, used as a photorefractive recording material, is again sensitive in the blue-green, but it's not, if you're trying to make a focusing element or something like that, you run into a problem at longer wavelengths if you're trying to use it at longer wavelengths. So you could use the CGH approach again to correct for that. But if you didn't have the mask writing capability and all that stuff available, there's another technique, kind of an elegant technique, that is based on, again, this sort of looking at what the aberrations are for the hologram that's reconstructed at lambda 2 and designing a set of holograms that incorporate those aberrations. So you can do kind of the same thing that I mentioned in this other in this approach here, except that we do it for the chromatic wavelength difference. All right, and so for instance, what we want is some desired. So this is our desired phase function. For the image, right? So this may be, we're not going to be perfect, but maybe we can get it, we can get it down to a pretty small spot, again, which may be smaller than the resolution of our detection element that we're using, like the camera pixels or the resolution limit of your eye and so forth. So what you can do is say, okay, so if I know I can calculate what this phase function is, right, from the recording and reconstruction geometry, and I know this is what I want, okay? So now I can say that if I have, so what I want to correct for is the difference between the actual image phase function that's formed and the desired phase function. All right, and so this then is going to give us some delta phi p, or phi rho rather, where rho is, say, the this normalized radius value that we have away from the axis of our holographic system. Okay, and so this difference in phase now we can represent. Let's say our major aberrations are spherical coma and astigmatism. So we can now represent this as a set of aberrations where we have minus, say, an eighth times the spherical aberration coefficient, rho to the fourth, plus 1/2 times the coma, rho to the cubed, minus 1/2 times the astigmatism, rho squared. All right. So now we have, so these are coefficients, and they're also constants that are functions of the point source holograms that you would use to construct the, in construction, all right, to construct holograms that would actually form certain aberrations. And again, thinking back to like Zemax or the Synopsys code 5 programming, those simulation programs actually have capability to do this kind of hologram design for this corrective process. All right, so in order to do this more easily, I mentioned, when we first derived the paraxial relations for the holographic imagery, where we had x3, y3, z3, and x4, y4, z4. I mentioned that there's another formulation for kind of the ray tracing that was put forth first by a guy named Latta. This was there's a series of articles actually in Applied Optics back in 1971, actually on ray tracing when this was in computers. So this was like the first big ray tracing analysis of holograms. With computer systems and all this kind of stuff. And so he formulated another way of describing the formation of holograms and the reconstructed imagery using point source holograms. And this is based on kind of a different notation than what we had talked about before, but a much more convenient notation for doing this point source kind of reconstruction process. And correction process. And so in this, say, if we have this holographic lens, we now have a, say, here might be the reference point out here, and this is now described in terms of a a radial term here, excuse me, r sub r. So that's equal to the length of this distance that we have here, and an angle beta sub r relative to the axis, and then you would have, of course, you can have an object ray coming out. It also has a distance, depending upon where that object point is located, and a beta sub 0, and there could be an image now that's formed here. Here's r sub I, and a r sub p. All right, and a beta sub p. All right, so. So with this, the paraxial imaging, the complete paraxial, I gave you just along the axis the last time, but the paraxial image relations using this notation, and again, and also here, this might be, this is our rho that we mentioned earlier. So the paraxial image relations that we have now are, this was the equation I gave last time, was 1 over Ri equals 1 over Rp, and then we could have plus or minus mu, 1 over R0 minus 1 over Rr, where again mu is equal to lambda 2 over lambda 1. And the angular relation is sine of beta for the image equals sine of beta p plus or minus mu sine of beta 0 minus sine of beta r. All right, so this is a kind of an alternative set of relations that you can use instead of the Cartesian coordinate system that we had in our previous discussion for the paraxial image locations. All right, so now we have these this aberration function that we have here, which again describes what we need to produce to, say, pre-aberrate the hologram to get this desired phase function. And the spherical and coma and astigmatism coefficients can be written in terms of these in the following way. So we have for the spherical, this is equal to 1 over rp cubed plus or minus mu 1 over r0 cubed minus 1 over r cubed. The coma is sine of beta sub p over r sub p squared minus sine of beta I over r sub I squared plus or minus mu, which is again lambda 2 over lambda 1, times sine of beta 0 over r0 squared minus sine of beta r over r sub r squared. Okay, and finally we have the astigmatism A. This is equal to sine squared of beta p over r sub p minus sine squared of beta sub I over r sub I plus or minus mu sine squared of beta 0 over r0 minus sine squared of beta r over r sub r. Okay, so the idea then is to have or to force S, C, and A to be less than or equal to, say, some epsilon, which is a small dimension, to bring those aberrations under control. Okay, and so now as well, you can see in each of these relations we have really a set of point source hologram locations that are given by these various subscripted values for r and beta. All right, and so there was a paper written by a researcher named Amitai, and so the way. Okay, so let me just say I'm not going to have any questions, any real major questions on this on the on the midterm. Okay, so I know this is a little bit more esoteric, but the process in doing this looks something like this. So in the end, so here's the end hologram. So this is the final hologram up here. Okay, and so this is going to be reconstructed with, say, a point source, which is here at lambda 2, and it's going to generate the image phase here also at lambda 2. All right. Now, and so what you need, though, is you need a hologram that's pre-aberrated by the right amount. And again, all of the holograms can only be formed at lambda 1. All right. So there's actually two sets of construction paths that gets to that endpoint. All right. So these holograms here, these are with regard to the reference beam, to pre-aberrate that reference beam, and these over here again, are for the object. Notice here's an object phase and a reference phase. And so what you end up doing is you kind of make a set of secondary holograms that are used in cascade to finally construct this final hologram. Okay, so here, for instance, you'd use, here's a reference and object wave that would be recorded with a certain degree of correction to kind of reduce those aberration coefficients. Then you reconstruct it here with this VP, it generates this VR, and then you have another phi-O coming in. That forms another intermediate hologram, which then finally produces at lambda 1. So this is at lambda 1, and this is also at lambda 1, produces the final reference field that you need through, as going through these intermediate holograms. And here also we have two intermediate holograms that generate this final phase step, producing a pre-aberrated field. So again, kind of an interesting approach. Again, I would probably do this with a CGH rather than go through all of that. But it's, again, it's another approach that you can use. Yeah.
I have two questions. When you use this technique, do you have an idea about how much light can get through on the final hologram?
Well, okay, yeah, that's a good question. So, and the answer to that is you can get quite a bit of light. And the reason for that is, again, remember, you're not going to have a setup with these three holograms in. These are made, so this hologram is made in process. This hologram is made in process. Same with here and here. So the final hologram is formed, illuminating these holograms and getting the diffraction efficiency for just one hologram. All right, so you may get 90% diffraction efficiency coming through. That then illuminates the final hologram. You just vary your exposure time to maximize the efficiency, and your final hologram could be 90% or more as well. Okay.
Also, if we want, let's say we have an image that has two waves of spherical aberration, and we go through this process, and we go through this process, and we only code one wave of spherical aberration, whatever we're working on. When you get the output image, does it just do a simple cancellation at that back end, so you see the one wave of spherical aberration, or does that have some other effect?
Well, if you generate that one wave, then that's what you would be able to correct in the reconstruction.
But it is just like a lens correction where you just have aberration cancellation in your observation.
Yeah.
Okay.
So again, and the reason why this works too is that you're recording it, in this forward direction, but you actually say would be reconstructing it in the conjugate. So you're again eliminating those aberrations during the reconstruction portion of that. Much like that example I gave prior to discussing the wavelengths.
Okay. Sorry, I'm going to ask one more question.
Yeah, sure.
Can you use a volume hologram where you have
You can, and
stacks of these systems and kind of one, I guess like a summation of these systems in one volume hologram? Is that possible?
well, you need to have certain degrees of freedom for the correction. So if you were trying to correct for 3 aberrations, so we need 3 holograms. Okay. So it may be a little bit difficult to do that in this technique. However, for the CGH correction technique, you can do it in the one hologram and then reconstruct it in the same way that we saw here, right? So then you would just have, say, this field here would be pre-aberrated by the amount to correct for that wavelength difference. Okay. You may need, so in that sense too, in some of these cases, what you would have to do in order, because remember, there's 2 things we have to satisfy too. We have to get high efficiency, and so if you're going to change the wavelength, you could either encode that efficiency correction in the CGH by changing the angle of that beam, or you can change the angle of your reference beam that you're going to use with that.
Okay.
Okay. So again, it's not, it's not a trivial process, but there are some methods of correcting for a lot of these aberrations in it. So, and again, it utilizes a lot of the aberration coefficients, and these formulations here are much easier to use for those point source reconstructions. Okay. All right. Well, so that kind of finishes what I wanted to say about imaging, holographic imaging. And so the next subject I want to talk about is coherence. So we actually had kind of a thing come up in the lab where, again, so we were trying to record a holographic lens, and so if we put the beam splitter here, and so this then allows the beam to pass here, and then if we wanted to put a lens in this, we could do that and have our hologram here, the film plane, like so. And now we want to bring the reference beam in. So we could think maybe we could do it like this, where we have a here's our laser coming in, and so we put a mirror out here and do it like this, and then we can get our 20 degrees that we were wanting in here to do that. Now, the problem is, this path length here is much longer than this path length, okay? So in holography, you have to, it's interference recording, right? So we have to pay attention to these path length differences. Otherwise, you're not going to get a hologram being formed at all. And as a matter of fact, one of my students set this up in the lab, and so we had a little session on why that doesn't work. And actually, before I went back to grad student, I was looking at this, and I was spending a little bit of time working at National Bureau of Standards, which is now NIST, out in Gaithersburg, Maryland. And so I was looking at a study, or some analysis done, where if you had a two-mode laser, we'll actually derive this later. If you have a two-mode laser, so here you have frequency 1 and frequency 2 that are stable, as you vary the path length, the fringes that you would get, if you look at the visibility of the fringes and say this is delta L, path length difference, the fringes would start out high and then they would go down and then come back up and go down and so forth. So, and again, so the fringes, if we set up an interferometer, you'd see some nice fringes here. Here there would be no fringes. Here there would be fringes, and then no fringes. And so my student who set that up, I said, so he actually set up an interferometer and did this in the lab, and I did it too back when I was prior to grad school and everything. And it really does work. It's really kind of interesting to see that you have fringes, nice sharp crisp fringes, and that's what you have, say, 0 path length difference here. But as you start to change that path length difference, there's a washing out of that visibility. So this is a very important consideration that you have to pay attention to. And so if you recall, the system that we ended up with is not to use this, but to put another mirror there, right? And then to equalize these, first form an interferometer, and then you could put your lens, say, in this beam here, and then by adjusting these two mirrors, you can change the angle that you need pretty readily in getting that system set up. So again, it was a pretty good lesson for all of us. And again, a really important consideration. So so again, if we have a system where we have two beams, all right, we have some degree of coherence. So if we have two fields here, as we saw before, and say V1 is equal to E to the J phi 1 and V2 is equal to E to the J phi 2. If we go through and calculate this out, we end up with basically 2 times 1 plus cosine of phi 1 minus phi 2, right? So there, if we were now to look at the visibility, which is V, the visibility is simply I max minus I min over I max plus I min. And so the actual visibility that we would see is something that goes like from 2, and then it again goes down to 0 and back up again. If we had, so this would be with a visibility equal to 1, and as the, if we don't have, if there's a problem with the phase difference being, say, constant in this, what will happen is this visibility will start to decrease. And if we had incoherent light, this would just be equal to I1 plus I2, where I1 equals V squared and I2 equals V2 squared. All right? And so in this case, this would just be equal to 2 if I1 if the magnitude here is both equal to 1. And so in that case, we would just have a constant value for the intensity as a function of, say, this is our path length difference here. So this would be equal to L, say, the path length difference between those in, say, an interferometer or in our phase difference across the system. Okay. So again, we want to have high visibility in the system, and so there's two forms of. So in order to have high visibility, we want the coherence, whatever that means at this point, to be. We want a high degree of coherence. Again, what relative to what, and what does that mean? Well, high degree of coherence relative to the incoherent case. So here again, so incoherent means we have this, and we basically lose this term. Or let's write this as so we have I1 plus I2 plus I1 I2 cosine of phi minus phi 2, and let's see. So that would be our. And I think there's a 2 over here, or yeah. Okay, so this would be a coherent case, where we have this oscillation that we would see in the intensity, and here we don't see any oscillation. It's just a constant intensity that we have, which is the sum of all the intensities illuminating our detector. All right, so as far as coherence goes, we can break this down into a temporal coherence and a spatial coherence. So these are actually kind of different properties of sources that we would encounter. And so let's look at temporal coherence first. So for temporal coherence, what are we talking about? Well, if we had a source out here, and let's say it's producing a field that's propagating out in some distance, so this direction here would be, say, the k vector that we have, or the Poynting vector for that field. If we were then to sample this at 2 locations, so sample it here, and doesn't really matter where we sample it. We sample it at 2 locations, some distance apart at P1 and P2. So if we have that, so here's our source. We have the field propagating, and we sample it at distances that are further and further apart. When these fringes that we would see wash out, okay, that would be an indication of what the temporal coherence length is for that source. So when we talk about coherence, it's really with regard to a source. And again, so we have a temporal coherence length, okay, which is going to be equal to C times a temporal coherence duration. So this field, you can think of it another way, is that this field can be considered monochromatic, or an ideal source for a period of time or for a distance of propagation. So temporal coherence is coherence along the direction of propagation. And most of the time, we're going to be worried about temporal coherence with holography. Okay, there's a couple of situations where we're going to have to worry about it as spatial coherence as well. But most of the time, we're worried about temporal coherence, and we can measure it using an interferometer, which is pretty easy to set up. Maybe I should have you guys set one up in the lab during the next lab or something like that. So here we can, one form of interferometer which works very well for measuring this is a Twyman Green. It's kind of a variation of the Michelson interferometer where you have planar waves illuminating the system. And so here you have the planar waves coming in. You have a beam splitter. It splits the beam into 2 paths, all right? So that's what we need. So here we have M1, and then we have beam propagates out here to M2, and we hold, so we hold one of these fixed, so the beam comes up and down. This beam goes out and back as well, and then they recombine. All right, and so we have both beams coming in, and then we look out here, and we'll see on a screen out here, we'll end up with some sort of, we'll see these fringes, all right? And so this visibility that I mentioned here, this Imax minus Imin, is a measure. What you're doing here is measuring the contrast or the visibility of these fringes. So, and then what you do is you keep increasing this distance out here, and so the coherence length, L sub C, is, say this is very crisp, very sharp fringes, and then they wash out. So that distance, so you're actually getting 2D, right, because the beam goes out and back. So if you move this back a distance D, it's, the coherence length is twice that distance because of that. And so you'll see these nice sharp fringes at one point when you're within the range, when these are, say, very closely matched in separation distance. Say that's the starting point. But then as you start to move that back, you might see fringes again that kind of start to wash out like that, and eventually, in some cases, it'll actually be just a constant value. All right. So one thing too, though, in order to see this, these fringes like this, you're going to need to tilt one of these mirrors a little bit. Okay. Otherwise, you'll just see you can still see a fringe, but it's just going to be one big dark spot or a bright spot, which is a little hard to see. So, if you just tilt one of those mirrors, which isn't hard to do, usually it is tilted, you'll see these nice sets of fringes that are much easier to measure, for instance, as far as contrast. And another thing you can do too easily is just put a lens in that beam and project it onto the wall so you can see a nice big figure of your fringes, okay? So again, the temporal coherence is looking at the coherence length along the direction of propagation. So what do we mean by that coherence length really? Well, what that means is that the phase at P1 minus the phase at P2 is a constant for each separation distance that we have, okay? So this phase difference, if it remains constant, is going to give us a contrast value in that interference term, okay? If not, if it's varying or changing, say, in time, then it's going to wash out. We're not going to see it, okay? So what about, so that's the temporal coherence. What about spatial coherence? Well, so temporal coherence is the phase, registration along the direction of propagation. And so this is the kind of the coherence that we would see across the wavefront. So here if we have a source and it propagates, we have, say, an extended source, so let's make it a big spot. The field emanates from that source out here, and then we sample it at 2 points across the wavefront. So here we have P1 and P2, and again we're looking at phi of P1 minus phi of P2, and so when is that equal to a constant? The difference in distance between P1 and P2, this gives us the spatial coherence length. All right, and so the one example of that is is kind of the Young's slit, or the Young's slit experiment is one way of measuring it, just like you have this Twyman green. Here, if we have so let's see, the simplest maybe example of an extended source is 2-point sources separated in space. So let's take, here's S1 and S2. And so this is actually a combination which is kind of representing this extended source, or let's call it spatially extended source. All right, so we could think of a very simple extended source as 2-point sources that are radiating at the same wavelength, okay? And so now we put a screen here to sample the wavefront, okay? So we have a screen, and we put our two sampling points here, P1 and P2, separated a distance d apart. And so here we have, light comes in this hole, and in that hole, there and there. And then we let the light propagate out to a screen. Right? So we have the light there and there. So if we say stop the light coming from this point source, all right, what we would see is a kind of a nice fringe out here. Again, this single wavelength propagating, and we would get a nice set of fringes caused by, the spacing of those fringes would be determined by the separation distance between those two holes in that screen. But now if we let this other source propagate as well, right? Now, so here's from lambda, or from S1. For S2, it's going to be slightly, say, shifted, right? And that's going to correspond to this distance here. All right, and so we end up with slightly shifted, another nice set of fringes, but they're shifted, okay? So if we look at the sum of those, we're going to end up with something like that, right? So we have this kind of reduced fringe contrast. Now, what if we had kind of the same setup, but we increase this separation distance out here like that? All right, so we have the same source located here, S1 and S2, and the screen's out here. So now if we have this, say, D2 greater than D1, what will happen now when the light goes through and off to this screen is that we're going to get a higher frequency fringe from each one of those, and the second one's going to be shifted. And so when we add those two, we're going to get a much smaller variation in the contrast out there at the screen. All right. Okay. So again, so we use the kind of this double slit to measure the spatial coherence, and we'll use a kind of a standard interferometer to measure the temporal coherence. All right. Okay, so let's now look at a couple of different cases for spatial coherence. All right, so let's say that we have, again, so we have two fields. So we have V1 is one field, e to the minus j 2 pi nu 1 times t, and we have V2 e to the minus j 2 pi nu 2t. All right, and so our intensity, again, we do a coherent summation of those. We end up with I1 plus I2, and then we have plus the time average, right, of V1 V2 star plus V1 star V2. Okay, kind of writing this out a little more formally. And so this then equals I1 plus I2 plus twice the real part. Since we have a number, a complex number and its conjugate, right? That gives us twice the real part of that number. So we have V1 V2 star. Okay, just from our complex field notation. So this is another representation of the interference equation that we talked about where we had cosines before, but this form here lends itself a little more to some formal analysis. All right? So what is this? So what we need to look at is what is this real part of the V1, V2 star, all right? Because that's going to give us the magnitude of the visibility characteristic for this system. So this real part of the time average, V1, V2 star is equal to what? That's equal to, again, a time average. So we have the real part of 1 over 2t, where t is our time that we're going to do the averaging over. So in our case, you know, as far as the time that we'd be interested in, it might be, say, the exposure time for our hologram, all right? And so here we have integral minus t to t exponential of j 2 pi, and I guess I'm using nu 1 and nu 2, so we have nu 1 minus nu 2 for the frequency t, and that's integrated over dt. Okay, so that kind of looks familiar. That's just the Fourier transform of a rect function, right? So we end up with here for this form of a function simply that this is equal to sine of 2 pi nu 1 minus nu 2 times that averaging time t divided by 2 pi nu 1 minus nu 2 times t. All right? So again, so we will have good fringes provided this has a non-zero or a significant value. So that will go to 0, though, when this t is, say, much greater than 1 over nu 1 minus nu 2. Okay? So again, this is just a sinc function, and so it has a functional form that looks like that. And so we can take the limit, say, for this, and this again is plotted as nu 1 minus nu 2. So again, so when nu 1 times t is setting our limit here, that will give us an idea of what the coherence time will be if we have a, say, a difference in the two frequencies for the recording beams. Okay? So that frequency is not going to be, that frequency difference cannot be very much because, again, if it is, then we're going to find that this time is going to be very, very short. Okay? So you can see here, too, if the frequency difference is 0, this time that we'll have, you know, high interference for is going to become infinite. All right? So we start to see now, you know, this inverse relationship between the spectral bandwidth, right? So this might, we can consider this to be the spectral bandwidth of our source and the time over which we're going to have high coherence, or a region where this term remains significant, okay? Which again is that term which is representing kind of the coherent oscillation of that visibility characteristic, okay? So that's one case where we have, say, two different frequencies. So A here is we have nu 1 not equal to nu 2. All right, whoops, not equal to. And now let's look at another case. So what if we had nu 1 equal to nu 2, but let's say that there's a phase difference between the two, and there's a slight time dependence of that phase difference. Okay, so we can represent that as, now we have nu, or V1, V2 star. This is, again, exponential of minus j 2 pi. They have the same frequency, nu. We can call that nu 1 times t, but we have also this phase term, phi of t here. Right, so we have need that j like that. All right, so that's our nu 1, nu 2 star, but we need the time average of that, right? So if we take the time average of that, then we find that that just goes to 0, right? Because if that is changing in time, that part is going to cause the fringes to wash out. Okay, there's no, as I mentioned before earlier, you know, when I started, we have this phi of p1 minus phi of p2 equal to a constant, but in that case the phase is a function of time, and so that will kind of wash out. Okay, now there's another situation as well to look at. So The third case is, what if we have a monochromatic source? So a truly monochromatic source is going to kind of emit a plane wave or some wave at the same wavelength for all time, okay? But let's say instead of having it emit for all time, we truncate that, all right? So we now have a pulse of monochromatic light. So here we have delta t for that that kind of shutters that monochromatic source, and it's at a frequency nu sub 0. So we can represent that field as, again, V here is going to have say it has a magnitude of A0, e to the minus j 2 pi nu 0t. And so we have that when t is within this range here. So let's zero, take the center of that. So it's from minus delta t over 2 to delta t over 2, and v is equal to 0 for t, say magnitude greater than delta t over 2, plus or minus. Okay. So so that kind of sets the range, our field that we have, and we can do this kind of the same process now, where we look at this function that we have, and now let's do one other thing though. Instead of just looking at the field, if we take the Fourier transform of that, we end up with the frequency spectrum for the source, right? So if we have V of, say, nu is equal to the Fourier transform of V of t, all right, then we can say that if we take V times V star, this is equal to, say, the power spectral density. And this is going to describe to some degree, what the spectrum of that source is going to be, all right? So the advantage of doing this, and so this is going to be equal to V squared, the advantage of doing that is that we can now measure this spectral density for the source, and we can kind of ascertain what the coherence characteristic will be from that. Okay, so we'll do the same thing again. I'll finish this next time, but we'll then take the time average of this V of nu squared, and we can relate that to the coherence time for that particular source, which is a pulse source this time. Okay, so I'll finish that up on Thursday.